Okay, we'll do the same thing with review number 2. I'll walk through it problem by problem, and I'll timestamp each question, and that way you can buzz to each one if you want. Anyway, the first one comes in at 13 seconds. In the scatter plot of y versus x shown above, the least squares regression line is superimposed on the plot. Which of the following points has the largest residual? So we have to remember the residual then is going to be the difference between the observed value and the line is made up of a bunch of expected values. So that residual then becomes that largest distance. So out of all those points, A is the furthest off that line. So therefore A is going to have that largest residual. Okay, 48 seconds. Which of the following points has the greatest influence on the strength? Okay, so what we have to remember is width provides strength. It provides C here is providing a lot of direction. If C wasn't there, this would be a fairly flat line through here. So therefore C, actually I was going to write a note up here. The residual is going to be the observed minus the predicted. And so therefore here we have to remember that width provides strength and in the terms of R. So therefore C is going to be that point that provides the widest width. Okay. Number 3 checks in at 139. There is a linear relationship between the number of chirps made by striped ground cricket and the air temperature. A least squares fit of some data collected by a biologist gives the model the following, where x is the number of chirps per minute and y is the predicted temperature in degrees. What is the estimated increase in temperature that corresponds to an increase of 5 chirps per minute? So what we could do is we could come up with any increase of 5. So if we started out at 9, we could use 14. If we started out at 10, we could use 15. Put both of those in for x and solve. But really, we could just take 3.3, which is my slope. We're going to take it times 5. And that difference there is going to be 16.5. You'd arrive at the same exact answer if you used the 2 points. But that was just a shorter way to get through there. So that one's going to be B. Okay. 4 checks in at 236. The equation of least squares regression line for the point on a scatter plot not pictured is y hat is 2.3, etc. What is the residual for the point 7? So what we have to remember when we see this is we're going to consider the 7 to be the observed value. From number 1 up there, we'll remember again that the residual is equal to the observed minus the predicted. So what we have here is asking us to find the residual, so that will be of known. I observed a 7, however, I need to figure out what my predicted value is. So we'll have to do a little bit of, we'll have to plug that value into my equation for that. So if I come over here, that is I'm using my linear regression equation here. 2.3 plus 0.37 times x, in this case my x value is 4, and that's going to give me a 3.78. So my predicted value is that there. So that means we're going to come over here and put 3.78, and we'll subtract those to get a 3.22. So that turns out to be A. All right. And number 5 checks in at 356. Which of the following would not be a correct interpretation of the correlation of R? So typically we say R provides strength and direction and how much, whether it's linear or not. Okay. So we know that this is going to be negative and on the weak side. And so therefore we just have to figure out which ones we'll go with this one. The variables are inverse related. Okay. This is actually going to be true since it's a negative slope. We know that one variable increases while the other variable decreases. So that's what that's what causes a negative slope. So therefore, as one goes up, the other one goes down. So therefore, that's going to be an inverse relationship. Okay, the coefficient of determination is 0.09. So we had to remember what that coefficient of determination is. The coefficient of determination is r squared. So we're going to take that negative 0.3 and we're going to square it, and that turns out to be 0.09. So that one's going to check. 90% of the variation between the variables is linear. If we come over here, we just got that. That's talking about r squared again, but r squared is not 90%, it's 9%. So here's our one that's got an issue. This is actually going to be 9%. Therefore, C is going to be my answer. We already talked about being weak, and all of the above are not correct. So that's what we'll end up with there. All right. Number 6 checks in at 550. A real estate company is interested in developing a model to estimate the prices of homes in a particular area, the metropolitan area. A random sample of 30 recent home sales is in the area taken for each sale. The size of the house in square feet and the sale price of the house in thousands of dollars is recorded. The regression output of the linear model is shown. What percent of the selling price of the home is explained by the linear relationship with the size of the home? So we have to remember when we're talking about what percent is going to be r squared. So, and actually they give it, remember the r squared adjusted we ignore. So we're going to go with the r squared value is 0.908. So this one, no work to it. We just got to circle letter C and we can move on with life. Okay. Number 7 checks in at a 646. Using the information in question 6 above, what is the equation of the least squares regression line? So again, when we look at this, my constant, okay, that is going to be my y-intercept is there. The variable here, the size, that is going to be my explanatory variable. The number out to the side of that is going to be my slope. And so now we have pretty much all the things that we need. As far as we really just need the slope and the y-intercept. My slope is going to be 0.123, so that has to be the variable here. My slope, so it's going to be next to x. And we said that that constant is going to be my y-intercept at 13.465. So that means that D is going to be my correct answer. In number 8, checking in at 750. The correlation between x and y equals 0.75 if both x and y scores are converted into z-scores, and the correlation between the z-scores for x and the z-scores for y will be, and what we have to remember is correlation is unaffected by unit change. So therefore, my correlation was 0.75, and it continues to be 0.75. All right, 828. A data set, X and Y, has a correlation coefficient of 0.65. A second data set B, has a correlation of a negative 0.65. Then, which one do we know? So really, one is going to be 0.65, so that means that it's going to have a positive direction, and it's going to be a moderately strong relationship. This is the same moderately strong relationship, just in a negative direction. So really there's no difference between the two except their direction. So the points in A are stronger than B? No. The points in B are stronger than A? No. A and B exhibit the same strength, same linear association. And we talked about that earlier. They do exhibit the same strength, just in a different direction. So C is going to be my answer. One of the data sets is exponentially related. Have no idea. You can't tell which data set is stronger without seeing the data or seeing the scatter plots. And again, we've already arrived at C, so that was just a reminder there. All right, moving it up to 9. 9 checks in at 934. A least squares regression line was fitted to the weights versus so weights in pounds versus age in months of a group of many young children given by the following regression line. The residual for the prediction of the weight of the 20-month child in this group is negative 0.46, which of the following is the actual weight in pounds for this child. So again, we're going to go back to that equation that we talked about earlier. There's actually, I might have overdid it on this review for residuals, but oh well. Residual is going to be the observed value minus the predicted value. So we talked about, they gave me the residual. It says the residual is negative 4.6. We can put that in there. The observed value is what we're trying to find. What is the actual weight of that child? The predicted value is something I can find because I know my prediction equation. And so we're going to drop then, with this is for a 20-month-old. So we're going to go with 16.6 plus 0.65 times 20. So that is going to be my predicted value, and that turns out to be 29.6. Okay, so that means that we're going to add the 29.6 to the other side, and that's going to leave me with 25. All right, 10 checks in at 11:18. Referring to the residual plot below, what can we conclude about the following? So remember, this is going to be a residuals plot. I'm never going to be asked to make one, but you might be asked to interpret one. Again, when we interpret that residuals plot, we're looking for a pattern. If that residual plot has a pattern would indicate non-linear. No pattern is going to indicate linear. Okay, so the data is approximately linear because no pattern is evident in the residuals plot. Well, that just nailed it right off the bat. So we'll take A and move on. Not linear because there is no pattern. Again, that's opposite of what we need. It's approximately linear because the obvious pattern, we don't see a pattern. And it's not linear because there is an obvious pattern. Again, there was no obvious pattern. So they all had their issues. We just had number A and went with it. 1223. A sports medicine surgeon is interested in the relationship between the range of motion of baseball pitchers and the number of years playing the sport. Based on this collected data, the least squares regression line of y is given, where x is the number of years playing baseball, and y is the number of degrees of motion in the player's pitching arm, which of the following best describes the meaning of the slope of the regression line. So again, my slope is going to be that coefficient of x, or my explanatory variable. It's negative 171. And we have to remember what x is. X is the number of years. So this is for every additional year. The response variable, y hat, which in this case is range of motion, will decrease by 1.71. So that's what we're shooting for. So again, for every additional 1 year. So for each increase in 1 degree, so A and B are out because they were talking about the increase of the wrong thing. C, D, and E all talk about the increase of 1 year played. There's an estimated increase in this. So this said the increase in degrees of motion. Well, that's wrong because it's negative. We need a decrease. And remember, this is going to be a predicted value or an estimated value. So this does say the number of degrees of motion decreases by 171, but this uses that deterministic language that we really don't want to use. We got to make it fuzzy. So that's why we have to talk about an estimated decrease. So that's why E is my good answer and D is not. Okay. So we got to remember that when we go ahead and define that or write that out, we're going to be estimated. Okay. All right. 12 checks in at 1408. This one's a little bit harder, and I suppose I don't have my. So this is going to be from our formula sheet. Okay. Again, we're going to have some formulas that we're going to use as far as our descriptive statistics. We use this one, which gives me the definition of a slope. We use this one to figure out what probably my y-intercept is, and then that one we've used all the time as far as that's my prediction equation. But in this particular one, they gave us the data points. we said that the mean of the x values is 5, the mean of my y values is 10. That gave me a standard deviation for 1 as well. So that means that we're going to use this guy here. We know that my slope is going to be equal to my correlation times the standard deviation of y over the standard deviation of x. So that came straight from our formula sheet. We were given that my r value is 0.6. The standard deviation of y was 10. The standard deviation of x was 4. We're going to multiply all that together and get a 1.5. Now we have a slope. We're going to need a y-intercept. So that's when we go use the other equation. Y bar equals a plus b times x bar. So we're going to use both the standard deviation and the mean of my x and my y to get my equation. So we know that y bar was 10. We're stealing that directly from the information. A is going to be my unknown. We just found out that b was 1.5, and we know that x bar is 5. So again, we are just pulling the information, even on this one. 0.6 was the r value. The standard deviation of y was 10. The standard deviation of x was 4. So just making sure we get those in the right spot. Okay, so we're going to multiply that. We're going to multiply 1.5 times 5, so that's going to be 7.5. We'll subtract the minus 7.5 to the other side, and it turns out that A is 2.5. So that means that my equation is going to have a y-intercept of 2.5. My prediction equation is going to be 2.5 plus 1.5x. And that guy is sitting there right there at C. All right, 13 checks in at 1634. We have a prediction equation where y is the estimated raise and x is the performance rating. Which of the following statements is not correct? Okay, so for each increase of a 1 point in performance rating, so remember my performance rating was x is the performance rating. So for each increase in 1, the raise will be on average 2,000. So that's what that is. For every additional performance rating, my raise will go increase by 2,000, so on average. So A is good. B, this equation produces a predicted raise with an average error of 0. Now that just sounds ugly. I mean, that's going to be our winning answer, but let's go look at the others. A rating of 0 will yield a predicted raise of 1,400. So if we put a 0 for x, we're going to be left with 1,400. So that checks out. The correlation for the data is positive. Well, it did not give us the R value, but because I know my slope is positive, my R value has to be positive. And I know not all the above are true because that B was just, this equation produces a predicted raises with an average error of 0. And that would mean that we have, I mean, it didn't tell us what R is, but that average error of 0 is going to be odd. That just doesn't sound right. All right, 13 is done. 14. So now we have some free response questions that we have to take ourselves through. So it looks like 14 is checking in at 1814. It wants us to construct a scatter plot. So remember when we're going to make a scatter plot out of the data. When we make a scatter plot, remember we're going to scale and label each axis. So this is the atmospheric ammonia. And on the x-axis, so again, we're using our swine population. We had to figure out a scale. I'm going to go from 0.38 all the way up to 1.85. And in my key, I decided to go by 0.25. Again, your scale, it's a personal preference on what you put for a scale. That's just what I chose to go by. To get me out there, scaling the y-axis, again, I decided to go by 0.1. Nothing written in stone that it had to be those. But there's what we and now it's just plotting those points, all right? 0.38 and 13. So here's going to be 38 and 13 is going to be roughly right about there. 50 and 21. So here's 50 and here's 21. 60 and 29. So here's 60 and we got to get to 29. 75 and 22, so 75 and 22. 95 and 19, 95 and 19. A little dip in there. 1.2 and 26, 1.2 and 26. 1.4 and 36. 165 and 37. 180 and 33. And 185 and 38. So there we go. We've constructed something. It obviously the relationship between as swine. It looks like as swine population increases, the atmospheric ammonia has increased as well. There appears to be a positive relationship between the two. So that's all that wanted to do was construct a scatter plot. So remember, I am actually surprised, and maybe I should have put that in the review. If we are asked to describe, and I'm going to add this now, as far as we may be asked to describe this. Okay. So remember, this is going to be where we, SOFA is the acronym that we used. Okay. And remember, we're going to talk about the strength of it, any outliers, the form, whether it's curved or linear, and then the association direction. Direction, form, and scatter would be the short way through that. But anyway, so we know that this is going to be a positive, linear, no outliers, and it's going to be moderately strong. We haven't got to an R value to it. I don't want to drop that in my calculator. Again, it's the test is going to be based on simple calculations, so they're not going to ask us to drop that into a calculator. But we want to write that out in sentence form instead of just doing all that. Well, actually, in reality, no, as long as we put this in context. So if we said the relationship between swine and atmospheric ammonia is, we would be covered. Okay. The value for the correlation coefficient for this data is 0.85. Interpret that value. So again, R is going to tell you strength and direction and linearity. So the relationship between swine population and atmospheric ammonia is, okay, 85 is strong, it's positive 85, and more than likely it is linear with that strength. Okay, so we've described R value. Let's see, based upon the scatter plot in part A and the value of the correlation coefficient in part B, does it appear the amount of atmospheric ammonia is linear related to the swine population? That is yes. Because the scatter plot shows a roughly linear relationship and the R value is 0.85, that would indicate it is strong. Okay, D. What percent of the variability in atmospheric ammonia can be explained by the swine population? So again, that's going back to that value is an R squared value as far as what percent. Well, that percent is generated from R squared. I wasn't given R squared. I wasn't given a computer output either. However, they did tell me that the R value is 0.85. So we're going to take 0.85 and we're going to square that. So 0.85 squared is 0.7225. And So therefore 72.25%. Now it just asked me for the percent of variability, but I'll go ahead and write it out in our sentence. 72.25% of the variability in my response variable, which is atmospheric ammonia, can be explained by the least squares regression line between atmospheric ammonia and swine population. And E, the equation for the line of best fit is given to us. Ammonia hat is equal to 0.15 plus 0.11 swine population. Interpret the slope and the y-intercept. So again, for each additional 1,000. So we have to remember that my swine population, up in the context of the problem, was in thousands. So for every additional 1,000, we'll say hogs, 1,000 hog increase in swine population, the predicted ammonia, atmospheric ammonia level will increase, because it was positive, by 0.11 parts per million, and we need to make sure we get that on average in there. All right, and so that's my interpretation of the slope. We got to do the y-intercept. If there were no swine, so again, there were no more swine. It's 0 for the swine. 0 for the swine population. If there were no swine, the atmospheric ammonia parts per million would be 0.15. So again, and it's getting through those sentences. This was the awkward chapter. It involved a lot of writing, but we need to go back and review how to define those. Alrighty, moving on to the next page. I know we're not through this problem yet, just so we have a time. We're looking at 28 minutes right now. Not that I'll put that in there anywhere, but how would you check to make sure a linear model is really the best model? Okay, we want to make a residuals plot. To see if a pattern exists. What does the least squares regression line equation mean? It is a line. So remember, as we pull this back here, there are many different lines that I can draw through here. We could be high, we could be low, we try to shoot it down the middle here, something like that. What we're trying to do is we're trying to reduce the square of the distance. So I'm going to have some positive residuals, I'm going to have some negative residuals, and my goal is to minimize the amount of, and we square those because some are positive and some are negative. We square them. So our goal is then to limit the amount of squared vertical distance. Okay, so that's what we're going to do here as far as not if, it is a line that makes the vertical distance of the predicted value to the observed value as small as possible. I probably should have taken that off the review. Not a big fan of that question, but since I put the review together, I can say that. All right, a population of 9,500 hogs gives a residual of negative 0.063. So again, we're going to get up to this residual thing. What is the actual amount of ammonia level? So again, we go back to it. A residual is equal to the observed value minus the predicted value. So again, it said that my residual is negative 0.063. The observed value is what I'm trying to find. I'm going to predict 9,500 hogs will be 9.5. So that number out here is going to be 0.15 plus, going off that equation from the other page, 0.11 times 9.5. And so that turns out to be 1.195. So we're going to have 1.195 over here. We're going to add that to the other side, and 1.132 will be the observed amount of ammonia, and that'll be parts per million to get a label in there. So don't forget our labels. And flip it around, and then what is the residual for? So again, another, get these down. The residual is going to be the observed value minus the predicted value. So here we're finding the residual. I observed a value of 0.3. Prediction-wise, again, my equation was 0.15 plus 0.11 times my thousands of swine. So in this case, it was 1.5. And that turns out to be 0.1665. So we put that number over here. We subtract and we get 0.1335 parts per million. All right, and that takes care of question 11. Okay, let's see what type of damage we can do to question 12. Checking in at 3217. The computer output below is a mini-tab regression analysis for the first and second test scores of 30 students in an AP statistics class. Write the equation, the prediction line, making sure you define your variables. So remember, if we wanted to, we could define what y hat is, and we could define what x is, which is perfectly fine. I personally like to write out what my variables are. So if we come over here again to remember what we have here, your constant is your y-intercept. So there is my y-intercept. Test 1 is going to be my explanatory variable. This is going to be my slope. We didn't really get into it. Actually, we'll get into the next problem. S, this is my standard deviation. And r squared, we definitely want to know what that is. And remember, to get to I'm going to extend this problem a little bit, because if we wanted to get to an r value, we need to take the square root of 0.136. And so if I square root 0.136, we get 0.369. But remember, an r value shows direction, positive or negative, so we'd have to go back and look at my slope. And if you wrote plus 369, you might luck into the right answer. But if my slope were negative, I'd have to make sure my r value was negative as well. But that's just the different things that we get. And since we did not do too much, there's a p value over here. If we did, never mind. I'm going somewhere where I don't need to go. Anyway, so remember, we're trying to then predict. Use the computer output to write a regression analysis for the first test and second test scores of 30 students in an AP Stats class. So we're trying to predict test 1 is my explanatory variable, so that means that test 2 has to be my response variable, and then we're going to predict test 2. So we're going to put a hat over it. My y-intercept was 28.26, so if I got a 0 on the first test, I'm going to get a 28.26 on the second, which seems a little amazing. But anyway, plus 0.4865 times my explanatory variable, which is my test 1 score. So we have created a prediction model. And again, we could have written that if you'd have wrote, we could have written that as y hat equals and x, done that with the same thing, but you had to define what y hat was and define what x is. Interpret the standard deviation in the context of the problem. So my standard deviation, we talked about that. That was 11.78. Okay, so the typical variation, I like the word deviation better. I don't know why I wrote variation in there. The typical deviation from the least squares regression line of test 1 versus test 2 is 11.78 points. And we can always top it with on average just to make that fuzzy. Okay. Does the linear fit seem reasonable? Why or why not? I'm going to say no, it's not. So again, we're going to go, what are we going to look at? We're going to look at my r squared value. This is only going to, the test 1 used to predict test 2 takes out 13.6% of the variability. So we're going to say no because the r squared value of represents 13.6% of variability is removed by using test 1 to predict test 2. Because we could just go with an average of, the average of test 1 is going to be the same as the average of test 2 and go from there. And so that's only removing 13.6, so it's not a whole lot. And again, we're going to finish up with another residual question. Suppose you know that one student scored 80 points in the first test and 90 points in the second test. Calculate the residual. Explain what the residual tells us. So we know, again, the residual, let's go one step further. It's the observed value minus the predicted value. So we're trying to find the residual. We scored on the test 1 was 80 points and test 2 was 90 points. So we observed a 90-point test score. We need to get that predicted score. So we're going to go up to the top and grab that equation. So test 2 hat is equal to 28.26 plus 0.4865 times whatever score we got on test 1, which in this case was an 80. So that is going to be a 67.18. Wow, we're way off. 67.18. And we're going to get 22.82 points. Now, we also have to explain what that residual means. So we ended up with a positive residual. So that means a positive residual means that the prediction line, the least squares regression line, underpredicted the test 2 score, and you probably can't even see this. My bad. The least squares regression line underpredicted the test 2 score by 22.82 points. And we'll leave it at that. All right. So 39 minutes. So that wasn't too bad. Anyway, there you go. And we'll shut her down.